In class, the last couple weeks, we've been discussing a variety of different integration techniques, integration by substitution, integration by parts, and so on. But now we're going to take a look at a different situation. I've got a function f of x equals e to the minus x squared, and I want to compute the area between the curve, the x-axis x equals 0 and x equals 2. Well, of course, this is just the integral from 0 to 2 of f of x dx. Now, to compute the value of the integral, we have to anti-differentiate e to the minus x squared. And we could play around trying substitution and all sorts of things, but it's not easy to find an antiderivative of e to the minus x squared unless you actually cook one up using the second fundamental theorem of calculus. In other words, let your antiderivative be the integral from t equals 0 to t equals x e to the minus t squared dt. Recall that the second fundamental theorem of calculus allows us to create the antiderivative of any continuous function. The problem with this antiderivative, though, is that for purposes of evaluating this integral, substituting 2 and 0 in and subtracting, it doesn't really tell us anything. In other words, this is an antiderivative, but it's pretty useless for purposes of evaluating that integral. It's not helpful. So what we're going to do is we're going to look at numeric approximation techniques, building upon what we did in Calculus 1. For the sake of simplicity, I'm going to actually look at a different function. It's a nice smooth curve that goes up like this. In fact, it's just a parabola. We know how to estimate the area under the curve using different types of Riemann sums. So just as a refresher, I'll first look at the right-hand Riemann sum. We're integrating from 0 up to 3. I'm going to choose a delta x equals 0.5, which means I'll have 6 rectangles. Each of the rectangles has width 0.5. And then for a right-hand estimate, I use the function output at the right-hand endpoint of each subinterval. So 0.5, I look at that height. 1, I use that height. 1.5, I use that height. 2, I use that height. 2.5, I use this height. In 3, I use this height, which is up at 9. So again, the width of each rectangle is 0.5, and the height of each rectangle is going to be the function output at the right-hand endpoint of the subinterval. Now you can see that the vertical dash marks are divided into quarters, but I'm only using delta x equals 0.5. So I'm going to estimate the function outputs. I'm going to estimate at 0.5. It looks to me like the function output might be, say, a quarter. That's a rough estimate. There's 1.5, so we'll say 1/4 there. At 1, the function output is pretty clearly 1. At 1.5, the function output appears to be, I'm going to say 2.25. At 2, the output is 4. At 2.5, the output appears to be about 6.25. And then at 3, the output is 9. So this would be our right-hand Riemann sum R6, and if I evaluate this, I get 11.375. And you can see how I've shaded my rectangles above. And if you look at those rectangles, the area of those rectangles combined exceeds the area under the curve. So in this case, R6 overestimates the true value of the integral, and that's because f is increasing throughout the interval 0 to 3. Okay, the function is increasing throughout the interval from 0 to 3, so these rectangle heights are always going to be above the curve, and we're going to be including some excess area in our estimates. Now let's do the same thing with left-hand Riemann sums. Let's do L6. So in this case, delta x is still going to be 0.5, and I'm going to use the function outputs at the left-hand endpoints of each of the subintervals. Now, the only difference between this and R6 is that I will be using the function output at the first left-hand endpoint, which is 0, and I won't be using the function output at 3. 1, 2, 3, 4, 5, and then there's a 6 rectangle with no area there. So the integral from 0 to 3 is approximately L6, And if I go through the same sorts of calculations, I get 6.875, I believe that is. In this case, L6 underestimates the true value of the integral. And that's because f is increasing throughout the interval. We're failing to include little portions of area from rectangle to rectangle that fall under the curve. So that's the left and the right estimate. We talk about these in Calculus 1. Now we're going to do something different. We're going to look at the midpoint sum. Instead of using the function output at the left-hand endpoint or the right-hand endpoint of each subinterval, we're going to use the function output at the center or the midpoint. That's why I have hash marks of separated by a quarter. So again, delta x is going to be 0.5. Now what I've done is I have to estimate the function at the midpoint of each of my subintervals. So I have to estimate f at 0.25, 0.75, 1.25, 1.75, 2.25, and 2.75. And I've done that by looking at the graph because I have very good vision. Well, and I also know the formula for the function is in essence a quadratic. And this is what I get for my function outputs. I add these together, multiply them by 0.5, I get 8.975, and what I've done is I've drawn the rectangles here. Now you can see for each rectangle I'm overestimating. I'm including some area here that I don't want to include. This area is not below the curve, but then I'm leaving some out. And you might think that the amount that I'm over and underestimating by from rectangle to rectangle, they might cancel, but we have to be very careful about that. No, that's not going to be true in general. In this case, we got a midpoint estimate of 8.975. If you go back and look at the left and right estimates, you'll see that this number is between the two of them. In this case, M6 is less than R6 and greater than L6 because the function is increasing throughout. Now we've used rectangles, but now let's take a look at something different. Let's take a look at trapezoids. So here's a picture of a trapezoid. I'm going to be looking at one trapezoid in my partition. So I've got xi here, xi plus 1. The width is delta x. Now the area of a trapezoid, it ends up, is the base length, which is delta x. And then I multiply that by the average of the two heights. So this height would be f of x sub I, and this height would be f of x sub I plus 1. That's actually pretty easy to show that it's the average of the two heights. What you can do is break this trapezoid up into a rectangle and a triangle, write down the sum of those two areas and simplify. So the area of the trapezoid would be delta x times the output or the height at the left-hand endpoint plus the output or the height at the right-hand endpoint, and we divide those two by 2. We average them. So let's go and apply this to this situation. We're going to estimate we're going to do the trapezoid estimate T6. Now we're going to have to average function outputs. So what I've done is I've made a table of values of function outputs. These I had from before. I use these for my midpoint. I use these for my left and right estimates. So the first set of outputs would be 0 and 2.5. That's that height plus that height. I'm going to average them. Then I'm going to take the next pair of heights, 0.25 and 1, and average them. So that's that plus that averaged. 1 and 2.25, I average those, so that would be that height of 1 plus this height of 2.25 averaged, and so on and so forth. The last height would be 6.25 and 9 averaged. And when I compute that whole quantity, I get 9.125. Now I can graph that by doing the following. I can draw a trapezoid between each pair of successive points. Now my graph does not bend too well, so it's kind of hard to see the points that I'm using, but I'm drawing a little segment that goes from one point to the other. So there's a little bit of area tiny bit of area that's trapped in here that's being included in our estimate, but that's not under the curve in this particular example. Now, if we go back and if we look at what L6 was and R6, L6 was 6.873. R6 was, trying to hunt the value down, R6 was 11.375. So it ends up that L6 and R6, if we just average those two sums, we get the trapezoid estimate T6. So if you've already computed the left-hand and right-hand Riemann sums, you can just average the two of them to get the trapezoid estimate. Okay, here are some things to observe. The trapezoid estimate T sub n using n trapezoids is always the average of the left and the right. Because it's the average of two numbers, it always has to be between them. It's the average of two numbers will always fall between those two numbers. So if f is increasing, we know that the left-hand estimate has to be less than or equal to the right-hand estimate, and the trapezoid is going to have to be trapped between the two of them because it's the average. Of course, we already know that if we have an increasing function, the left-hand estimate is less than or equal to the true area under the curve, which is less than or equal to the right-hand estimate. But this does not tell us whether t sub n is greater than or less than or equal to the integral. There's something else going on there. If f is decreasing, things switch. The right-hand estimate is less than or equal to the left-hand estimate. The trapezoid, because it's the average estimate, has to be sandwiched between the two, and we know the true value of the integral is less than or equal to the left-hand estimate, greater than or equal to the right-hand estimate. But again, we don't know the relationship between the trapezoid and the midpoint estimate. So let's take a closer look at that. When is the trapezoid estimate greater than or equal to the true value of the integral? Let's consider this by just considering a prototype trapezoid in our partition. So I've got a point x sub I here, x sub I plus 1 here. And notice how I've drawn the curve. I've drawn the curve like this. It's bending up. It is concave up. And because it's concave up, because the graph is concave up, I'm including some area under that trapezoid which is not included under the curve. This would also be true if the function was concave up and increasing. The idea is that if you take two endpoints, your 2 points in the partition, xi and x sub I plus 1, and if you connect the outputs with a chord, it's always going to fall above the curve. So it's always going to include some area that we don't intend to include in the true value of the integral. So when f is concave up on the entire interval from a to b, not just a part of the interval, the entire interval, the value of the integral is less than or equal to the trapezoid estimate t sub n. So to summarize, if f is increasing throughout the interval from a to b, increasing, we know that L sub n is less than or equal to m sub n is less than or equal to r sub n. We also know that the true value of the integral falls between L sub n and r sub n. But f has to be increasing throughout the interval. If it switches from increasing to decreasing, we can no longer make this conclusion. If f happens to be decreasing throughout AB, these inequalities just switch directions. The trapezoid estimate is the average of the left and the right. It always falls between ln and r sub n. If the function f is concave up on the entire interval from a to b, the trapezoid estimate is an overestimate of the actual value of the integral. We saw that on the previous page. What is not as obvious is there's a similar result for the midpoint sum. If the function is concave up on the entire interval, the midpoint estimate m sub n is less than or equal to the integral from x equals a to x equals b to f of x. And that is not obvious from the picture, but it is in fact too. And if the function is concave down on the entire interval from a to b, these inequalities switch directions. Here's an example for you to try in preparation for class. Take a look at the function e to the minus x squared. Estimate the integral from 0 to 2 using the left-hand estimate L4, R4, M4, and T4. And what you should do to get started here is to make a table of values at 0, 0.5, 1, 1.5, and 2. So do that in preparation for class.